Switched reluctance motor drives. Switched reluctance machine is a specific kind of doubly silent machine. The switched reluctance motor drive is becoming attractive for electric vehicle propulsion. Following are the reasons: low system cost, robust machine structure, reliable converter topology, simplicity of the control, and high efficiency. Also, it has some drawbacks. Large torque ripple is the one drawback. High machine non-linearities and the large acoustic noise produced by the switched reluctance motor are few of the drawbacks. We can see the working principle of reluctance motor. The main concept is the reluctance of the magnetic circuit depends upon the air gap. By changing the air gap between the rotor and stator, we can change the reluctance of the motor. In switched reluctance motor, the stator and rotor have projected poles made up of soft iron and silicon stampings. So this can be seen here. So this is the stator, this is the rotor, and both have the projecting poles. So this is the projection, and this is the projection for the stator, and this is the projection for the rotor. Silicon stampings are used to reduce the hysteresis losses which are occurring into the iron portion or silicon material. The rotor does not have winding. As you can see here, no winding is there. And also there is a winding on the stator, but rotor is without any winding. And stator only carries the main field winding. Each winding in the stator is connected in series with opposite poles to increase the MMF of the circuit. So it is called phase winding. So phase winding is there on the stator. For example, here A and A dash is the phase A winding. B and B dash is the phase B winding. C and C dash is the phase C winding. So it is a 3-winding motor. Here we can see the block diagram of the SRM, switched reluctance motor. There is a control circuit, digital controller. So here is the SRM. Motor speed is given to the digital controller. Then the controller will decide the converter circuits input to the SRM. And also it maintains the proper waveform for phase A, phase B, and phase C. And here we can have the input source. So input waveform is modulated as per the requirement of the SRM. And the control circuit always collects the information of the rotor position, and based on that, controller gives the input to the motor. Here we can see the switching pulses for different phases: phase A, phase B, and phase C. So supply is given to the winding means it is turned on. For other instant it is turned off, then on and off. So phase sequences are properly maintained as per the requirement of the speed of the SRM. In general, switched reluctance motor drive consists of 4 main components: switched reluctance machine, switched reluctance converter, sensor, and controller. SR machine plays a key role, that is conversion of electrical energy into mechanical energy or mechanical motion. SR converter is powered by DC source as seen in the earlier diagram. A DC link is there, and a DC link can be there, and it can be also powered by a battery pack. So these three ways can be applied to provide the power supply. Switch reluctance machine is fed by the switch reluctance converter, which is generally different from the inverter used for AC machines because it required the required waveforms to be given as input. The controller feeds driving signals to the power devices of the converter in accordance with the command signal, control algorithm, and sensory feedback. So controller has to control the signal appropriately and maintain the phase sequence and the magnitude so that the SR motor can give the required torque and speed. With the use of proper control strategies, high performance can be achieved in the switched reluctance motor drive. This block diagram shows the basic configuration of SR motor drive. Here we can see the diagram where this is a DC source, then SR converter is there. This is the SR machine, switched reluctance machine. So position and current, these are sensed and given to these sensors. These are the input, and then it will give input to the controller along with the command signal, and it will control the input to the SR converter or the switching of the SR switch reluctance converter, and required input will be given to the SR machine. Now we can see few SR motor drive configuration. This is a single switch reluctance motor drive configuration. The single motor configuration has the merits of using only one switch reluctance motor and one switch reluctance converter, which can maximize the corresponding size, which can minimize the corresponding size, weight, and cost. So here only one SR machine is there connected with fixed gear, then it goes to the differential, and then it will drive the wheels and the vehicle will be driven. Since a differential is needed to adjust the relative speeds of the driving wheels for rounding a curved road, the use of mechanical gearing is inevitable. The SR machine is normally designed for high-speed operation, typically over 10,000 RPM, so as to reduce the size and weight. So as the speed increases, the size will go on reducing. So it is designed for high-speed operation. To match the wheel speed, typically less than 1000 RPM, the fixed gear is used as shown here to step down the switch reluctance motor speed about 10 times, and it will be suitably given to the wheels. Another is the dual motor SR motor drive configuration. So here you can see dual motor SR drive configuration, high speed gear structure, this is the first one, and low speed gearless structure, this is another. So for high speed, here gear is used, here gear is used, but here directly SR machine is coupled to the wheels directly. So two wheels are there and two machines are connected to these wheels. The dual motor is prepared when taking into account the system complexity and cost. So obviously system complexity and cost will increase because we are using two motors, related controls, and related accessories. The dual motor configuration employs two SR machines separately power or independently. Differential action can be electrolyting the bus. Here the differential is also can be independent can manage turning of the of SR machine talent for actually teeth, the stator and rotor and teeth. Really her teeth and then talent called multi-phase is concentrated winding in windings. There is without any wind. There are many possible to machine. There and road. Here you can see one configuration. First, three phase 6 by 4 plus 6 4 the outer is the 1 5 and are better port by the yellow is better 6 5. Also here you can see 4 phase. Here A, B, C are the three phases in the earlier logic. You can see A, B, C are the 4 phases. Actually A dash B dash right. So A dash B you can see 8 by 6 volt 8 stator pole. Here we can measure from here this 5 6 by this phase 6 by 4 advantages for cost by 4 cost and better phase balancing capability for have the best balancing. However, it suffers from higher torque ripple. There will be ripple in the torque and there will be also noise produced. On the other hand, the 4 phase 8 by 6 better starting torque lower torque ripple power devices and higher converter. As for each phase, supply has to be given proper more and higher converter there and complex. Here you can see a different logic. In order to improve the torque density, SR machine can adopt multiple teeth per stator pole. So A is one stator pole. Instead of having the single teeth treated like this. Here it has been completed here. Multiple teeth per pole teeth are there. Figure shows phase A, B, C dash, B dash, phase A, B, C, and 12 by 10 pole SR machine with teeth per stator pole. Teeth per stator. This is one pole. Likewise, you can see there are six pole T and six pole. You can see there are 12 teeth per pole. Based on the principle that use of two stator teeth can theoretically double the torque production, same electric load, yet the torque production double can support. Multi teeth structure leads to the reduction of area of copper winding, decrease in inductance, difference between the aligned and unaligned position, decrease torque production. Is the advantage, that is copper winding, reduced area of copper one winding there, and decrease the inductance, the align and decrease and reduce the. Because of the merits of rubber structure, heat tolerance and flexible shape, yes, are attractive for in-wheel drive. It can be used drive, but using separate gears can be in the outer rotor topology is at the outer side. There the rotor was at the outer rotor, the outer rotor side which is there now. In particular, the outer rotor topology enables the rotor mounted with the rim of the wheel, hence eliminating the reduction gear and corresponding transmission. Directly, outer rim. So here you can see a three-phase 6 by 8 rotor SR machine. You can see here 8 poles. Here and 6 poles A, B, C, as well as 6 now are inside, but these are the stator. Written as 6 by 8 instead of differing from the conventional SR machine to that the rotor has smaller diameter than the stator is inside, and it will the outer rotor topology has a large rotor diameter. So the rotor is now side, then it is large diameter inside it. Here it is a larger diameter. Hence the number of rotor poles generally selected to be larger than a number of order to reduce the torque ripple directly imposed on. Generally, rotor is selected to be larger than the stator poles. Rotor poles has to large number of torque ripple. Here we can see more details. Torque production. Figure shows stator poles are wound with concentrated resistance. When they are excited with a current I, magnetic flux psi established. Flux versus magnetomotive force MMF characteristic is plotted for the unallied position between the stator and rotor. at theta is equal to theta 1 and the aligned position between the stator and rotor at theta is equal to here theta is equal to theta 1 and theta is equal to theta flux versus mmf. Can be seen that flux versus mmf characteristics for the unaligned position is almost linear. We can see here because the reluctance of the air gap is large, whereas the characteristics for aligned position non-linear because of the reluctance of the magnetic flux suffers from magnetic. Here we can see the nonlinearity when it is aligned. Because when aligned, there is non-linearity and there is a reluctance path, and it can have the saturation. So this is the unaligned portion, not aligned. So this is the completely aligned portion. Aligned portion. You can see here theta is equal to theta 1, theta is equal to theta 1 at this plotted. You can see almost the linearity, the flux and mmf. When it is aligned, you can see after a certain portion it will have linearity. So the mmf is increased, the flux will not increase linearly, it will lesser change. So in the magnetic set, theta 1 and theta is equal to theta. If you see the principle of star machine rotation, when the phase A winding is excited here, the rotor tends to rotate clockwise. Rotor will try to, if it is excited, rotor will try to rotate clockwise direction so that it will try to align. That is, it decrease the reluctance of the flux path until the rotor poles 1 and 1 dash align. This 1 and 1 dash align the stator poles A and A. So this will align with A and A dash. So it will try to rotate here. Reluctance of the flux path will be this flux is crossing from this core portion of air. It will have low reluctance. Then the phase A switched off. Once it is aligned, this phase A is switched off and phase B is switched on. So immediately phase B is turned on. So because of this phase B is turned on, the reluctance torque tends to make the rotor poles 2 and 2 dash align with the stator poles B and B dash. This will, as it is rotated now, position will try to align B and B dash, so it will have rotation. Similarly, excitation of phase C. Now phase C is excited. The winding is excited, which results in alignment of rotor poles 1 dash and 1 the stator poles C and C dash. So this sequence will attracting and switching on and off magnetize, demagnetize will continue. The torque direction is always toward the nearest aligned position. Hence, by conducting the phase winding in the sequence A, B, C, according to the rotor position feedback from the position sensor, the rotor can be continuously rotated clockwise. You can keep the rotation continuously, switching the switching sequence. On the contrary, by conducting the phase winding in the sequence of ABC, ACB, the rotor rotates anti-clockwise. So we can change the phase sequence by controlling the input or turning on and off sequence of the windings like ACB, rotate anti-clockwise. Here we can see this working. Along the variation of phase inductance with rotor position, there are five regions. So you can see the five sequences. If you consider rotor position theta 1, theta 2, theta 3, theta 4, and theta t, 1, 2, 3, 4, and t, you can see how the rotor position is there. So 0 to theta 1, this position. The stator and rotor poles have no overlapping. There is no any overlapping. It is the unaligned position. Stator and rotor is unaligned position. So here you can see this unaligned position, this aligned position, here aligned position. First, we are considering the unaligned position so that the magnetic flux and hence the inductance are minimum and kept constant. Thus, this region does not contribute torque production. There is no any torque production when they are unaligned. So here you can see the first theta 1 to theta 2. So from this to this second region, stator and rotor poles start to have overlapping. So they will now start aligning from theta 1 to theta 2. So the magnetic flux and hence the phase inductance increases with the rotor position, giving a positive change there in the inductance. So dl by d theta change in the inductance with respect to angle. Here we can see L minimum and L max will be. When a current is applied in this region, a positive torque is created for the motoring operation. So a torque is created here. From theta 2 to theta 3, if you see this position, the rotor poles completely overlap. Theta 2, theta 3, it is the overlap position. Aligned position, one can say, and the movement of rotor pole does not change the overlap. Corresponding magnetic flux and hence the phase inductance are minimum and constant. There is no change in the inductance, there is no torque production. You can see theta 2, theta 3, there is completely overlap. Change is there. There is no torque production. Theta 3 to theta 4, this next position. Stator and rotor poles start to reduce overlapping. They start overlapping from theta 3 to theta 4, so that magnetic flux and hence the phase inductance decrease. So there is a change L by d theta. One can from theta 4 to theta t, the stator and rotor poles are unaligned because here it is started unaligning and now it is completely unaligned here. That again phase inductance is kept constant, L min and no torque is put. This is the portion where torque is put. Theta 1 to theta 2 and theta 3 to theta. After the working, we can see application example of SR motor drive in electric vehicle. Nidec, a Japanese manufacturer of electric motors, have developed SR motors for electric. Z019 model can offer rated output power of 19 kilowatt and it can be up to 29 kilowatt. With a voltage of 170 volt, the motor can produce the rated and maximum torque of 3 and 86. Maximum speed 11,000 rpm. Key feature of SR motor is the reduction of vibration and noise by optimizing the shape of the rotor and stator for as well as timing of current control. At 2013, Geneva Motor Show, Land Rover used an EV powered by an SR motor drive. This EV was based on the Land Rover Defender model in which 70 kilowatt SR motor was 300-volt lithium-ion battery having capacity 27 kilowatt. EV can offer driving range of 80 kilometer per charge. Because of the SR motor delivering a starting torque of 330 Newton, EV simply adopts the single speed transmission gear ratio drive. The top speed achieved. This is the example of SR motor drive.